So we spent some time talking about the properties of parallelograms and what we can prove knowing that a quadrilateral is a parallelogram. Well, the next natural question is, what sorts of information can we use to prove that a quadrilateral is a parallelogram, even if we don't know immediately that opposite sides are parallel? And so, as a brief reminder, a parallelogram is a quadrilateral with both pairs of opposite sides parallel, and as a part of the first part of this module, we saw that opposite sides of a parallelogram are congruent. We saw that opposite angles of a parallelogram are congruent, and we saw that the diagonals of a parallelogram bisect each other. Well, as it turns out, any of those properties can also be used to determine that a quadrilateral is a parallelogram. This is not always the case. It's not always the case that a particular property can be used to definitively show that a quadrilateral is one particular subcategory of quadrilaterals. For example, if diagonals are perpendicular to each other, it doesn't say anything about the particular type of quadrilateral. It narrows it down, but it doesn't determine a single type. So we have to be careful when we're trying to use properties to prove that something or just say that something is a particular type of figure. In the case of a parallelogram, though, we can do that. So, for example, if opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Go ahead, pause the video, copy down this statement here, come back when you're ready to move on. So the next little bit of this video is going to be a little bit statement heavy, a little bit pause and copy heavy, but we're going to get through that relatively quickly and get to a proof of one of these to wrap up the video. The next property that we saw of parallelograms is that opposite angles are congruent, but we can actually take the congruent sides a little bit further to show that a quadrilateral is a parallelogram. So, for example, if one pair of opposite sides of a quadrilateral are parallel and congruent, they have to be both parallel and congruent, then the quadrilateral is a parallelogram. So go ahead, pause the video, copy this down, come back when you're ready to move on. Notice that this is slightly different from the properties of a parallelogram that we saw before. We can actually use, as this statement says, one pair of parallel congruent sides to show that the entire quadrilateral is a parallelogram. We also saw in the previous video that one of the properties of a parallelogram is opposite congruent angles. Well, as it turns out, if you have a quadrilateral that has opposite angles congruent, then that quadrilateral is a parallelogram. Go ahead, pause the video, copy down this statement, come back when you're ready to see the last one, and then go into one of the proofs. Finally, we know that the diagonals of a parallelogram bisect each other, and that's actually enough to say that a quadrilateral is a parallelogram. If the two diagonals of a quadrilateral do bisect each other, then we know that the quadrilateral is a parallelogram. So go ahead, pause the video, copy this down, come back when you're ready to see the last slide. So we have four potential ways of showing that a quadrilateral is a parallelogram, and that doesn't include the definition of it. If we have a quadrilateral where we know that opposite sides are parallel, we have a parallelogram by definition. We are using the properties of parallelograms, or the properties of particular types of quadrilaterals, to show that opposite sides must be parallel. And the proof that we're going to look at to end the video here is the one of opposite angles of a quadrilateral being congruent. So at this point, I'm going to invite you to pause the video and see what you can come up with on your own as far as strategies. If you get to a point where you feel like you're confident enough that you can do the proof on your own, I invite you to do that before unpausing the video and going through and seeing the proof. If you just are strategizing and are not coming up with anything right away, that is totally okay too. You are welcome to let the video continue rolling and see the proof and copy it down as we go. But go ahead and pause the video now, do that strategizing and proving for yourself, and then come back when you're ready to see the proof. Now this proof is going to be a little bit different, and that's why we're doing it in the video here. We're actually not going to use congruent triangles as a part of this, even though we potentially could in some ways. Instead, we're just going to rely on basic algebra, actually, as well as properties of parallel lines and transversals. So what we're given is that A is congruent to C and angle B is congruent to angle D. Again, I'm not going to write that in the proof for the sake of saving space on the screen, but that should be the first step of your proof. And we're actually going to do something here where we're just going to say, okay, great. If angle B and angle D are congruent, then we're just going to call them both X. because that's their measure. And if angle A and angle C are congruent, we're just going to call it both y. It's important that what we name these angle measures is something generic like a variable, because as soon as we put actual numbers to it, then it stops being a general proof and then starts referring to only one particular quadrilateral. But here, we're just going to name them x and y, not for the sake of saving space, but because we're going to see some algebra that gets us to what we want. So, if we have two angles in this quadrilateral that are measure x, and we have two angles in this quadrilateral that are measure y, something that we know about quadrilaterals is that the sum of the angles is 360 degrees. So in this case, if we go from angle A to angle B to angle C to angle D, then y plus x must equal 360. Why? Because there are 360 degrees in a quadrilateral. Great. Now we're going to do a little bit of algebra here. So x plus y being 360 means 2x plus 2y equals 360. And y, because that's just combining like terms in algebra. But now we can divide that by 2 using the division property of equality to get that x plus y equals 180. And I'm just going to write div for division property of equality, but that's what it is. We can just divide both sides of an equation by 2. It's something that you're very familiar with. Well, now, this is actually everything that we need, because we can look at angle x and y on the right-hand side of this quadrilateral and say, well, angle B and angle C are same side interior angles for lines AB and DC with transversal BC. So what does that mean? AB is parallel to CD because of same side interior angles theorem. Those two angles are supplementary. They are same side interior angles between lines AB and DC using transversal BC, so therefore AB and CD are parallel. Similarly, and that's why I left the space there, we can look at angle A and angle B as same side interior angles for lines AD and transversal AB. And so same side interior angles, x plus y is 180. Those two same side interior angles are supplementary. Therefore, AD parallel to BC. Again, because of the same side interior angles theorem. This, again, is a place where we want to be very careful that we are assigning same side interior angles, and in different cases, alternate interior angles, to the correct pair of lines with the correct transversal. It's very easy to get that relationship mixed up and say that the wrong set of sides are parallel. But that's how we can prove that opposite angles of a quadrilateral being congruent is enough to call the quadrilateral a parallelogram. We rely on those theorems that we saw before about parallel lines and transversals, and in this case, we can prove that same side interior angles are supplementary, giving us that opposite sides are parallel.